In this lecture, we're going to go through decision tree training for the verification layers. For VLSI design, we'll have basically 3 layers: the struct layer, parameter layer or layers, and also finally verification layer. There are some basic information that can be used to train the verification layer. The first one, the absolute sig parameter, usually have logic variation in the order of a few tenths of percent to 50 to even 100%. On another side, the relative sig parameter, which are based on rubric, can be controlled to have a beta, maybe the order of the magnitude beta. For example, we can even achieve maybe 0.1% accuracy. And typically for a small device, small size device, this number or mismatch or relative value could be in order of maybe 1 to a few tenths of percent also. On another side, device parameters are same getting worse when you're going through VLSI scaling generation by generation. And also reliability and aging effect also we say are getting worse. So now let's look into type 1 device model. Type 1 device model are actually used to model the worst case device violation of the different type of device. In this case, we are trying to emphasize on the similarity of same type device type, especially when you have a replica. And the key of the simulation is really trying to validate when different type devices are varying significantly. In type 1 model, a few built-in information for this training of this decision tree layer. The first one, if for the same type device, they are assumed they are exactly the same. That means there is no variation between same type device. And also device parameter is also time invariant. And also assume same temperature for all the devices, even though temperature may change, but every device get the same temperature. And same input for the power supply. Okay. In the corner simulation, actually there are 2 levels of the training to reduce entropy. The first level we call the probability biasing. In this case, even though the device parameters are varying in the continuously, which are distributed in the value. However, in order to simplify, or basically we lump this into basically 3 cases, like I'm showing here. That means since the device parameters are varying actually based on the assumption of the normal or Gaussian distribution. So we can look into actually 3 sigma. For example, typically we are using 3 to 5 sigma. If 3 sigma for each of the device parameter, we assume 99.7% of the year. Okay, in this case, obviously we can simplify the simulation from infinity case, which are have a distribution, into 3 cases of the nominal, mean, 3 or 5 sigma, mean, or 3 max. Okay. In this case, we can simplify the design simulation case for this parameter. Okay. So now, after this reduction, let's take a look at the one design example of using 2-stage open to see how many design cases we need. Okay. For this open, we have 8 most devices, and we assume each one can be could be very differently. Okay. That means in this case, based on the first reduction, we simplify into the, for example, VT become nominal, low, and high. This is 3 cases. And also the mobility, the beta, also you have low, high, and nominal 3 cases. Okay. And temperature, similar, low, high, and also nominal, like room temperature. Supply, low, high, and nominal. If you do that one, this basically come back to, for most devices itself, like a 3 times 3 times 3 with the power of 8 combinations if you simulate, okay? And also this circuitry also have one resistor capacitor. So in order to cover, also can have the same thing. That means 3 sigma or 3 to 5 sigma, low and high and middle. So that means we're gonna have 3 options for both capacitor and resistor, okay? And also we have temperature. In this case, if you combine all of those, we'll have totally 3 times 3 to the power of 2. So now after combining all of those combination, we got a syringe space for this variation layer to verify this 2-3 open. It's a very big number. That means it's pretty much 2.28 times with the power of 13. And also can calculate the entropy based on the syringe space size. It's about 44.3 bits. Okay. This simulation actually is too large. That means there are too many cases. Okay. So now let's look into something we call corner simulation. That means in corner simulation, we're going to use something we call pivot corner. Okay. In the pivot corner simulation, we assume PMOS and NMOS are very independently. However, all the NMOS are the same. We're going to vary the same, and PMOS will be the same. In that case, well, basically, okay. So this will call process corner. Okay. At the same time, and the process corner we're looking into is really relation of the like air effective VT and like all of this. So all of will capture into process corner. Okay. That means we'll combine all this one and we'll just look into the devices are fast or slow or maybe are nominal. Okay, so this is what we call P corner, process corner. In addition, this V corner, that's a supply corner. Supply corner, again, we're looking into a nominal high and low. And also temperature is T corner. So PVT, T is temperature, high and low. Okay. In this case, if I want to simulate this amplifier with PMOS, NMOS, well, basically we'll have a totally 5 process corner. That means we'll have tip corner, that's both A and P device are in nominal condition. And after we'll have a SS, that's both devices are slow. And FF, both devices are fast. And the SF and the FS, that means either P are slow and are fast, or N are fast, P are slow. Okay. So now let's look into after this PVT corner simulation, how much entropy will be reduced. Okay. So now for this two state open, first one will have 10 devices, but I only have 4 tags. So that means we'll have basically NMOS, PMOS, and also resistor and capacitor. And also, since now we assume same voltage, same temperature for all devices. That's a -40 or and either 120, 110, or 65, different design, and nominal, and the same power supply for all devices. That's a 3 case. Okay. So now let's look at syringe space. In syringe space, really, in the pivot corner, first one we're looking to is really basically for the most device, we'll have a slow, fast, slow, fast, slow. That's 4 options. And after we put an additional 2 voltage option, either extremely high, extremely low, and the temperature high and low. And for resistor, same machine will have low and high. And okay, and after we'll have basically okay in addition to all the extreme corner, we'll have one we call nominal or typical corner. So if you combine all of those, this basically come back to roughly around maybe 65, maybe corner. Compared to originally very large number like 2.28, like 13th power. Okay, so that means by corner simulation, really the solution space of the verification are highly reduced. Okay, and of course, if we can calculate entropy, it's only 6 bit. So that means corner simulation can be used to significantly cut down the Turing space for SIG validation or verification. Of course, in this case, we assume all the same device the same, and different types are different. This is really most VLSI secure, just like information of the same device or can tracking very well. So this gives extremely assumption. Okay. Since now the quantum simulation will not be able to catch the variation of the same type of device, this is a type 2 simulation need to kick in. So here are some very important information about the mismatch of same type of device. Okay. The first one is really, if you look at maybe for most devices, both VT and beta, both are inversely depend on the size of the device itself. Here, I will look at the standard deviation of the weighted standard deviation of this one will be proportional to square root of inverse proportional square root of the total area. That's W of A. Both are for VT and mobility. Okay. Of course, the coefficient of A is really depend on different technology. So, okay, here are some number which can be found from literature. Okay. And also, this is another piece of very important information. Is really the mismatch also increase or also depend on the distance of two replicator device. That means for same type device, which are they are close or they are far away, the mismatch also different. So this one basically come back to this equation. That means if you look at any parameter p, the standard deviation of this one are depend on basically, of course, this parameter could be VT or beta, but depend on the size of the device. Larger size is smaller at the same time, or depend on the distance. Okay. Due to this reason and the Monte Carlo simulation, this is type 2 modeling used to validate device variation. Okay. In this type of simulation, will emphasize on the mismatch effect of the same type of device. Okay. And also in order to cut down the basically the Turing space, we assume this standard deviation follow a certain distribution. That means, okay, by doing this way, the variation will not be changing independently. It's changing for a certain rule. This way, actually, this become like probability Bayesian. So that can be used to minimize the number of the case we need to simulate for the Monte Carlo or for type 2. Okay. So for type 2 modeling, there are a few building symmetry information in such kind of modeling. The first one, each device may vary independently, but however, the variation should follow some statistical distribution, for example, Gaussian. So these are used for probability Bayesian to reduce the cases. Second one, device parameter we assume in this modeling is a time invariant. Okay. And also same temperature and the same VCC for all the devices. By doing this way, we can significantly cut down the simulation solution space for the validation to the order of maybe a few hundred to 1,000. That's really okay. So now, type 1 and type 2 simulation did not cover the time varying part of the simulation or verification. But however, when you go into a deep submicron, even nanometer device, the aging review effect become increasingly important. In this case, we need to have a type 3 kind of model, something we call variability model to capture or to verify the time-dependent device variation. Okay, in this case, we're emphasis on the time device parameter change in time. Okay, this should cover both the short and the long-term behavior of the VLSI circuitry itself. Okay, and the second behavior based on the information or maybe the data is highly temperature sensitive. Okay, So now for the tapestry model, actually there are some built-in symmetry information in this modeling. The first one is device validation for setting aging mechanism offered by the physics. So that means this will come back to physics. Based on this one, we basically will have to we can't use this to cut down this maybe the simulation maybe actually solution space. Okay. So this is 3 type. Okay. At the end of the lecture, let's post actually question of the day. So this are something related to the topical talk come here, and you can use this one to have further learning. And also we're going to give the answer in the later lectures.